Hi everyone, as I said, I would not be here today. And I wanted to try to give this about just watch the video after I get done here. And I'll go through it. So directions are not the best for both of these. For A, what you're doing is trying to find the cross product of those two vectors. For B, you are trying to solve for just x on this. Okay, so do the cross product for A, and then solve for x in B. Okay, pause the video and give that a try. Okay, so if you recall cross product, and if you don't, here it is. The cross product is a 3 by 3 matrix where the first three vectors, or the first row is ijk, the second row is u, the first is u cross v, and the third row is v. And if you recall, what we do is we do I times this minus j times that plus k times that. And remember, it goes plus minus plus like I have there. So for I, what goes in the parentheses, what we do is we take I and we eliminate those two rows. And then we look at that 2 by 2, and we do 2 times negative 2, which would be 4. I'll erase that. There we go. So I eliminate the row in the column of I. We're left with 2, negative 1, 0, negative 2. So I have negative 2 times negative 2 is negative 4 minus 0, and I do negative 1 times 0. Then I go for j, I look at j, and I eliminate the row and column of j going down. I don't do that too much to mess up the number, so we'll need k. So I'm left with 1, negative 1, 3, negative 2, and we do the determinant of that 2 by 2, which is 1 times negative 2, which is negative 2, minus negative 3, or 3 times negative 1, which is negative 3, so that'd be plus 3. And then for k, we do the k, and we eliminate, and we have 1, 2, 3, 0, so 1 times 0 is 0, minus 3 times 2 is 6, and then we go ahead and simplify, and that would be negative 4i, that would be 1 in the parentheses, so I have minus j, and then minus 6k, and if you recall, that is the vector that's orthogonal to those two others. Now, why do we do that? Because that is finding the determinant or matrix of 3 by 3. We will find the determinant of matrix C, and in order to find the determinant of that 3 by 3, which is a cross product in terms of vectors, we also, within that, did determinants of 2 by 2. So that's what we're doing today is determinant matrices, and that's just to recall what we did with the cross product was actually finding the determinant of the 3 by 3 matrix, and I just want to recall that process. Okay, so let's turn those on. Yeah, we don't need to do advanced topic stuff. There we go. Okay, so I'm going to get rid of that. I'll have the completed notes posted with this video. We want to solve for x. So if we want to solve for x, b and d, we're going to have to multiply because b and d need not be factors. So like, let's think b is 2 and d is 3. We have to multiply both by each other. So if I want to solve for x, it means I want to eliminate y. So I'm going to multiply the top by d and the bottom by b. And if we do that, we get adx plus bdy equals ed. Multiply the second equation, bcx plus bdy, just writing in alphabetical order, equals bf. To eliminate the y's, we subtract, and we subtract the x terms would be adx minus bcx. The y terms will cancel, and then we have ed minus bf. Solve for x, we're going to factor out x. So we have ad minus bc equals ed minus bf. And then we divide, and we get x equals ed minus bf all over ad minus bc. Now, that would be the solution for x, for the general solution for a linear system. Why did I do that? Because if you look at the denominator, that is ad minus bc, if we go back up to our original equation, if we look at the coefficient matrix, it's abcd. Now, if I do AD minus BC as we have below right here, AD multiplied by each other. minus BC, that is the determinant, the exact same thing we did in the cross product. So that's what we're going to call the determinant matrix, and if you look here within the solution, if AD minus BC equals 0, then we would have X would be undefined, and we don't have a solution to the system. So that kind of gives credence to this determinant, what we're calculating, to be somewhat relevant, as we will find moving forward. Okay, so our goal here within these notes is to find the determinant of a 2 by 2 and a 3 by 3, and as we move forward, we are going to be utilizing this to actually solve matrices. There are many other applications of determinants. For instance, you go to equations of string theory to figure out like the path of the string throughout space-time, and you have the determinant of 2 by 2 matrices within those calculations, just like here. And of course, they show up in a bunch of other things, but that's the one I can think of off the top of my head. Okay, so that being said, if I have a matrix A, A11, A12, A21, A22, the determinant, the notation that we have here, that's one way we can write the notation for the determinant. The other way we can write it with is the bar around A. It's the first term times the fourth term minus the second term times the third term. And that's it. That's the determinant of a 2 by 2. Now, how do we do the determinant of a 3 by 3, excuse me, a 4 by 4 or higher? Well, we have, like we did in the cross product, that plus minus plus. Well, where did that minus come from for the J term? Why do we have that there? And when we did that in Unit 1 with vectors, I just said just accept it as it. But this is the reason why, because we have what are called minors and cofactors of a 3 by 3 matrix. And we'll go through this, and it's kind of tedious with the notation, but hopefully you're understanding what I go through, because wherever we see i's and j's, we're just plugging in whatever I equals 1, I equals 2, etc. We're plugging in j, and then that gives us a minor matrix, and it also gives us C, a cofactor matrix, okay? So, now, this formula was derived by some mathematicians long ago. I haven't seen the derivation. We're just going to accept it as is, but this does give credence to why we have a plus minus plus. And then if we have to determine, which you will be, determining the determinant of a 4 by 4 matrix, where the plus and minuses go for each of the terms. Like we have the negative in front of j, where will the plus and minuses go for a 4 by 4? And if we want to find the determinant of a higher matrix, where those plus and minuses go. So that's what this cofactors and minors does for us. Okay, so let's go ahead and figure this out. Okay, so what a cofactor is Cij, and it says if A is a square matrix, okay, n by n, a 2 by 2 or a 3 by 3, then the minor Mij of the element Aij, remember Aij is some element, it could be the first element, it could be the ninth element, it could be any element within the matrix. Mij is not a matrix, but is the determinant of a matrix. So the minor is the determinant of a matrix obtained by deleting the ith row in the jth column of A. And the cofactor is calculated as Cij. So eliminating the ith row in the jth column. So if we look up here, when we come back to here, when we have this, remember we had ijk here, if we have this Aij, which is entry 1, 1, we eliminate the first, the ith row, which would be, in this case, 1, and the jth column, that one, and the remaining matrix, we find the determinant of that. That is called the minor. And that's exactly what we did within the cross product, okay? And then C, the cofactor, is determined by taking that determinant and multiplying it by negative 1 to the I plus j. So what does that negative 1 to the I plus j do for us? Well, let's go ahead and take a look at it. Okay, so let's look at, if I want to find the cofactors of a 3 by 3 matrix and their sign pair. Well, let's start off with A11. Now remember, a cofactor, or a minor first, is associated, Mij is associated with an element Aij. So if I have element or an element or an entry A11, that's associated with minor 1, 1. Now I'll write it out explicitly. In this case, so we have A11, I equals 1, because that's our first one, and j equals 1. Okay? So what we do is we eliminate the ith row, which would be the first row in this case, and we eliminate the jth column, which is 1 in this case, and the determinant of that matrix is equal to M11. So M11, which is associated with A11, is the determinant of that matrix right there. Okay, so that would be the determinant of A22, A23, A32, A33. Okay, let's look at another one. Right now we're just calculating minors. Let's look at if I do A12. Okay, so if I go to A12 here, sorry, A12, A12, I'm going to cancel out the ith row, which is 1 in this case, and the j column, which is 2. And we're left with the minor, which is, since I is 1 here and j is 2, we're talking about the minor 1, 2, and that would be what's left over, A21, A23, A31, and A33. This is the exact same thing as, and then remember those bars, those long bars there mean determinant, just like we had in the cross product, and just like we have right here, in this notation right here, those long bars, which look like absolute value bars, means the determinant. Now, I'm not going to calculate that. I'm just trying to find these minor and getting comfortable with this notation. Okay, so let's look at the next one, A13. I'm not going to do any more than these three. Okay, and there's a reason for that. Okay, so now let's find the minor of M13. I cross out the ith row, which is 1. I cross out the j column, and I'm left with that matrix, which is A21, A22, A31, and A32. Okay? Now, those are our minors. Now, let's try calculator cofactors. Again, I'll rewrite the formula. Cij is equal to -1 I plus j times minor ij. Okay, so I calculated those three minors, M11, M12, and M13. So let's try to figure out C11. So C11 is going to be -1, and then we take -1 to the I plus j power. Well, I is 1 and j is 2, so that would be 1 plus 1 in the numerator, which equals 2 again. I and j right here, I equals 1 in this case, j equals 2, so 1 plus 1 gives us 2. Okay, so now we have minor 1, 1. Okay, so if you look, since -1 to the second power equals 1, that tells us that C11 is equal to M11. Okay? Again, we don't know how this minors and cofactors are going to help us determine the determinant. They will, but right now we're just doing these calculations to try and help us understand, to help us in the future determine the determinant matrices and where that comes from. Now let's calculate C12. Now C12 is equal to -1 to the I plus j power, and I is 1 and j is 2, so 1 plus 2 will give us 3, M12. Now, -1 to the third power equals -1 times M12. So we see when I plus j adds up to be an even number, then C11 is simply equal to M11 because -1 to the second or even power makes it equal. When I and j add up to be an odd number, note the row and the column add up to be odd, then C12 is equal to the opposite of M. Okay, so the cofactor is equal to M when the row and column add up to be even, and C, the cofactor, is equal to the opposite of the minor when I and j add up to be odd. That's what we want to gather from this. Okay, moving on. Now, the definition of the determinant. A is a square matrix of order 2 or greater, then the determinant of A is the sum of the entries of the first row of A multiplied by their cofactors. Okay, so we got a lot of nasty notation, but we'll break it down. First, that's the notation for determinant. That's the notation for determinant. This notation right here is sigma, that E-looking figure, and it goes from j equals 1 to n. Now, sigma means the sum of all terms that hold those properties. But we don't have to totally understand that. We'll get into sigma notation when we do sequences and series. If we look at that, that says entry A11 times its cofactor plus A12 times its cofactor all the way up until A1n, C1n. And A1n means we go up to the nth column, and multi and yeah, the end column. So the A1N would be the last entry of the first row multiplied by its cofactor. That's exactly what we did with the cross product. We took the I in the A11's point or position and multiplied it by the determinant, which was the minor axis. And then, okay, so it's like I times this was our first part. And then remember, our second part within the cross product was minus j. Well, j is the A12 entry. And remember, the cofactor, when I and j add up to be odd, is the opposite of the minor. And that's where we get our negative. Okay, so that's why we have that negative. So let's say if we have, and let me back up a step and remind you that what this says here, it says the first row of A multiplied by their cofactors. They say the first row, it could actually be any row or any column. So what you do is you take any row and any column and take those entries and multiply them by their cofactors, which remember are determinants of those remaining 2 by 2s, which go plus minus, depending on the sum of I and j. If I and j is even, then the cofactor is going to be positive. If the sum of I and j is negative, then it's going to be negative. I'm sorry, if the sum of I and j is odd, then it's going to be negative. Okay, so let's look at this. Let's say I have a 4 by 4 matrix right here. This 4 by 4 matrix right here, okay? So let's say that I want to figure out if the cofactors are positive or negative for each entry. So our first entry right here is 1, 1. So I go 1 plus 1, and that equals 2. So if I and j add to be 2, then the cofactor associated with that first entry is going to be positive. The second entry, which is 1, 2, row 1, column 2, 1 plus 2 is 3. Therefore, that entry has a cofactor that's going to be a minus. The third entry would be A13, that's an even number, I plus j is even, therefore the cofactor associated with that entry is positive. And we see we alternate from positive to negative. Okay, let's go to the second row. Second row, first column is right here. Second row, first column entry is right there. 2 plus 1 is 3. That's an odd number. So our first entry of the second row is going to have a cofactor associated with it that is negative. And you look, the next one would be 2, 2. That's even, odd, even. So if you look, these cofactor signs alternate from positive to negative. That's exactly what we have with a 3 by 3 matrix. So we pick any row or any column that we want, cross off the row and column that's associated with that entry, and find the cofactor of that matrix. So if I want to find, or the cofactor of that entry. So if I want to find the determinant of A, I'm going to do the first row. So the first row has an entry of 0, and 0, I cancel out that, and I cancel out that, and that leaves us with the matrix negative 1, 2, 0, 1. And that'd be negative 1 times 1 is 1, minus 2 times 0, which is 0. And note, I really have to do that because the entry 0 will give all that 0. And remember, since that's entry 1, 1, the cofactor of that's positive, and therefore you're positive out front. Now for the 2 here, which is entry 1, 2, that will have a cofactor which is negative, so we put a negative out front, and the entry 2 right there is 2, so that's our entry 1, 2, and then when we cancel out this, when we cancel out this, we have 3 times 1 minus 4 times, so 3 times 1 minus 4 times 2, so if I do that calculation, I have 3 minus 8, okay? And then we move on to the third entry, A13, which is 1, and since that's I and j add to be positive, that would be a positive cofactor, so I cancel out that, and I have 1 is our entry A13, and then 3 times 0, which is 0, minus negative 4 times 4, so 0 minus negative 4 would be 0 minus negative 4, which is really like 0 plus 4. And this first term is 0. The second term is negative 5 times negative 2, which would be plus 10. And then the last term would be plus 4. So the determinant of A is 14. That's how we calculate a 3 by 3 determinant. Okay, so that's your notes right there. I think you only have 2 by 2s and 3 by 3s. Now, if you have a 4 by 4 within there, when you cancel out one of the rows and columns, you're left with a 3 by 3. Well, you're going to have to do those 3 by 3 calculations 4 times over. So if, let's say, I have a 4 by 4 in our homework, I can't remember if there's one like it or not. Let's say 2, 1, negative 3, whatever. And then we have all these other terms right there. So if I need to do this times its cofactor, well, if I go like this, its cofactor is a 3 by 3. And you also have to do the determinant of that, 3 by 3, just like we did up here, and multiply by 1. Then you go to this one, cancel out that and that, and then you have another 3 by 3. Calculate that, and remember, your cofactors and for plus or minuses in front of the 1 and the 2. So the 1, the green one right here, would have a positive, that'd be a minus 2 because that's a minus. But you're going to have to determine the determinants of those 3 by 3s over and over again, and then add that. Do your best on them. Those are definitely challenging. I'll show you a better method of simplifying or what we using row reduction actually to make a 4 by 4 determinant more manageable. We'll work on that on Monday, and have a good weekend, and I will see you on Monday.